just wanted to recap a few things. I did download everyone's motherboard assembly, and I think it was interesting time spent, I guess, because some of the folks had 25, 30 files in the folder, and some had it in a zip, compressed zip drive, what do you call it, compressed folder, right? Is that the right way to put it? So that would have been great if you can compress your files into that, because then it will just one file, if not while watching TV, you have to click each file and then miss a few. That's what happened with that case, but it's okay. But I think all came through. Some of you gave me quizzes by writing the file name like BWT or something, and I have no clue who that but, if you name your files, name it like file name. Like I said, don't call it file.doc and underscore your last name. Like in my case, I may call it dot whatever it is, right? So at least that way I'll have some sense of whose work it is. And I also noticed that the Canvas has this default emails at tennessee.edu. I think that comes up with. So if you send me by that, I'm not able to download the file or look at the file. So please, when you send it to me, use my utk.edu address. Then it will come fine. So those are some things that I noticed. I got everyone's, and yeah, I sent you all a note saying this is what I'm missing, and then some of you immediately corrected or sent me if I was missing it. So except for one or two, I have everyone's work in. So I owe you now 2 graded works, the mini project and this one. Some of you already have submitted the sheet metal work as well, and some of you are submitting it. So we should have 3 things that have come in so far, then, right, as far as I can tell. Then the test you all are working on, and like I said, in the test there are several parts. You have to make some assumptions and work those into your assembly. If I were you, don't wait till the 15th to start working on the test. It might be a good idea to go at it slowly, right? As far as the other works, I've started uploading the things around the Ashby plots and the discussions what we have been having. So soon I want to assign that work as well. The stuff is coming at different paces for sure. And then, of course, the 3DS experience has been quite an experience so far, right? But anyway, let's take it in the positive light. And so where I was is in terms of the, I'll just continue at that point.
I had a question about
that. Yeah, please.
So as far as like, it lists what to submit. One of the things that it says is a material intent rendering. What does that mean?
Yeah, what I mean is that if you select the frame to be a nylon frame, then the rendering should represent its aluminum, for example.
Okay.
If the wheels are made of nylon, it may represent the nylon color. So the idea there is the customer has to not only see the geometry, but get a feel for what it may be made out of. The handles, if they're made out, the end caps are rubber, black, featuring textured rubber or something like that.
Okay.
That's what I mean.
Okay, that makes sense.
So last time I started talking about this, I think each of you now hopefully has access to CES Granta and have downloaded the EduPack. That should not have any issues like the software we're having on this. This is a pretty intensive software. That's why probably we are facing some issues comparatively. Once we go there, I would like you to start practicing the chart constructions on those. And so today, since we are a little bit already getting close to time, I will have to change my sequence of what I was planning to do. So let's reinforce the charts thing. And I'll complete my chain of thought next class. So this is from the chapter 3 of the handouts that focus on the material property chart. So remember, now I have done a discussion about the various properties in the theoretical sense. Right? We talked about the stress strain, toughness, force, deflection, Poisson's ratio, all the terminology, how that comes together, failure theories. We talked about conductivity and the electrical thermal conductivity factors, maybe magnetic permeability. So all those are the types of fracture toughness we saw, the K1C, G1C values, right, energy. Those are all things that you're always going to be looking back on when you're looking at different designs. And one thing today I was hoping to do, if you didn't take up so much time, was to go through that process. But generally when you start an application, you have to first set up what are basically called as the translations related to that product. By translation, and I'll explain this more in the next class, what we mean is what is the function of the part, what is the part doing, for example. If it's, that's like the first thing for you to understand, right? If this part is designed, what is that part going to do? What is it meant to do? Then there is the so-called translation-related objectives, right? And objectives are, constraints. So constraints means the part cannot be more than, say, 8 inches long, maybe a hard constraint. The part must exhibit these characteristics. The part must have high stiffness. It must have low deflection. It must have high thermal conductivity. It must have low magnetic permeability, or it should be an insulator, or it should be a conductor. Those becomes like your constraints, really, right? And then around that, you then start putting in what are called as the free variables. That means what is the thing in that the length has to be 8 inches, but do I have freedom in changing the cross section like I want to? I have freedom there. So I think the free variable could be the cross section. As long as the length is kept at 8 inches, I have freedom to do other things. Choice of a material may be a free variable. It means it's not mandated that you got to use this material. I could design for a material that essentially would meet those constraints and so on. So likewise for each product, we'll have to pick a product and decide on that. So maybe let's go ahead and do that. So this is going to be a little bit out of sequence of what I was planning to do, but let's do it in any case. So I'm going to take a CD case as an example. All of you know those CD cases, soon to be obsolete, but let's say in the prime days, you had the CD case, right? And the CD case was typically like basically a frame like that. It has a hinge and then it will open and close, right? Typically with this force. Most of the time this case is made out of polystyrene, right? Polystyrene for the reasons that it is very cheap for one, but what is the other attribute of polystyrene? It is
Clear.
Optically clear, very important. So generally in CD business, you want the product to be optically clear because you put labels in it, you put things like, so it's more to showcase the product on the inside. You don't want it to be, so in many cases these are called as jewel cases, far from jewel cases obviously, right? It's highly exaggerated name because as you know, if you drop it, this thing cracks. So it's not like a jewel by any means, but that was the marketing end of it. They would call it jewel casing. So there is an issue with that the product cracks, for example. It's very fragile, in other words, and many of you have experienced this, obviously, right? Most of the time these parts are injection molded, so I'm bringing in some process information along with it as well. Why injection molded? Any idea? Cheap. Very, very cheap. And because CD cases are produced in very large volumes, right? Very large quantities. Like throwaway prices, you hardly take a couple of cents for the CD case. Therefore, the process used is injection molding, which is able to give high quality finish, justifies itself for the cost of the tooling and everything, but it makes it so those are some things. Problems with this, like I said, these are general characteristics, right, of this product. If you take a product, these are general characteristics. Some of the problems that why you're interested in redesigning it, as I told you, this thing can crack ready, right? It cracks ready. It can jam shut, and all of us have seen that the hinges are usually plastic hinges, meaning it can fold. When you try to put it, sometimes it can shift, and then it's difficult to put it back in place. So that's what is called here jamming. Corners are sharp, so because many of you might have even cut your fingers trying to listen to music or something. Right? You try that is sharp corners because the attributes of polystyrene is it's very crystalline polymer. And if something is crystalline, it is generally brittle, it is sharp. And when we go into some more material discussions, we can talk about amorphous and crystallinity and all that. But those are all attributes within the material that you're trying to improve upon. So any product, if you look at, here the intent is to redesign. It's not to come up with a brand new product, but to take an existing product and redesign. So in doing so, you have to first break down the problem for translation factors, right? So translation has several steps to it. First one is you will have to define what is the function of the product. What is the function of a CD case? Exactly, contain and protect CD, correct? That's the basic function. It has to contain it and it has to protect the CD. What are some of the constraints that this product would require? As you can see, if you want to even to redesign, you still want it to be optically clear, because not many music people would buy it if it was opaque, right? So it has to still be optically clear, for example. You still want to bake it in large quantities, so you must be able to injection mold this, because that's one way you can increase volume and keep the cost down and quality very high. The other constraint is usually you make this in large bulk, so you should be able to recycle these things, because otherwise, as you know, it can really be, computer recycling is a big pain, as you can see, right? Now the bulk and bulk is accumulated, where do you put all that? To make this, why are you trying to redesign this? Because of some of those problems I mentioned. So you want to make it tougher than polystyrene. Remember, there's a difference between strength, stiffness and toughness, correct? Strength is essentially you're talking about stress. Modulus is stiffness. Here you're talking about toughness, means energy. Somebody just made a statement, if this GoPro falls, it will still be okay. Which means it has high toughness. It has energy absorption capability. If your cell phone these days falls, which falls often, it doesn't necessarily every time crack, right? Until you do it, go a little overboard, it won't crack. Which means it has a certain toughness built into it. So this is the same case in case of this CD here. The other thing is the dimensions have to be same or very similar as the existing case. It means you have a certain dimension constraint. So if you look at everything above dimensions, all these factors, right? All these factors could be thought of as function constraints, because they are associated with the function, right? If you talk about dimension, it's a geometry constraint, correct? Because it is associated with geometry. So in constraints, you have to identify what are your functional constraints and what are the geometry constraints. Every product would have a certain constraint that are tied to both these factors. So translation involves function, involves constraint, then it involves objective. What is the objective in this whole thing? Of course, after you incorporate all these constraints, you want to minimize or maximize. Usually an objective is associated with minimizing something or maximizing something. Obviously here you want to minimize what? Minimize the cost, right? You want to be able to sell it as cheap as you can, or be able to produce it, not sell it. There's a difference between cost and price, right? If the manufacturing cost for this you want to keep it as minimum, you can sell it for whatever you can sell it for. And the free variable here only happens to be then the material choice. Because he just wants to look and alternate that would give you those attributes, and you are free to choose what you want. So a translation involves 1, 2, 3, and 4. All these things have to be taken into account, right, when you are doing translation. So where those ASPE, these kind of charts will help you then is what are your design limiting properties. Once you have established your translations, what are your design limiting properties in this case? What will the charts help you determine? For example, you are interested in high fracture toughness, right? Toughness. So what gives you that fracture toughness? K1C. Remember, we talked about fracture toughness. So that is certainly a factor that you could look at. You also want to look at optical transparency, because translucency and transparency is a measured factor, right? Reflectance and reflections and refraction, all these things determine translucency. When you're designing eye lenses, transparency is very important. Also, you want to see your ability to injection mold, which means you need to look up some processing information from the charts, right? So that will have to be taken into account. And you also need to be able to evaluate recyclability from the charts. So sometimes as we go further, you can see the charts also give you a lot of embodied energy, the energy consumed in a certain process, CO2 footprint, all those are indications of the recyclability of the product. So these kind of factors, once you decide from these constraints, these are the key information you're looking for. Now you can know what charts you want to look at. Whether you want to look at K1C versus density, or K1C versus optical transparency. You can cross-plot fracture toughness versus optical transparency, right? And plot them out. And that gives you a whole options for you. And in that space, then you can start looking at what meets the fracture toughness criteria and how transparent is that going to be at the same time. So you can start picking up those things based on this exercise. So while you have thousands of charts to choose from, this exercise of translation gives you or narrows down what is it you need to focus on when you start looking at these charts. So that's how you use these charts, and not randomly you're trying to use them. So here, for example, density versus modulus may not be required because you're not really looking at that. But you do need fracture toughness versus maybe ability to recycle. That could be an option to look at. So as you take each product, you have to break it down into such exercises. If we have time, which usually is never the case, let us, I have 2 minutes. So if you got this right, I gave you CD case here. So I'm going to start with this example, right? And so this is a heat sink for microchips. So heat sink for microchips, right? And this is the electronic component, of course. All of you know that your computer has this big fan, right? And then when you get here, it's a small fan, but you can pretty much hear it. And you know that when that thing collects dust, slowly you put it on your lap, basically it gets very hot. So this heat sinks have a big role to play when you talk about electronic circuitry. So usually if you look at it, it looks something like this. It has this shape for sure. And does anybody know why this shape? Correct. The fins will increase the surface area, so heat can quickly conduct or dissipate from it. So usually the chips are sitting against it like so. So this is the sink, that's the chips right there. So usually you have a substrate behind it, and then you have these connectors that connect all of this, right? So this is your heat sink, this is the chip, this is the substrate, and these are like the connectors, the wires and the usual PCB connectors that go there. So as you know, the function of this, couple of things to note about it, general characteristics is to conduct heat. I mean, that's the attribute you want to have, absolutely. You want it to be electrically what? When you touch a computer, preferably you don't want to get a shock, right? Electrically conductive. So you want it to be insulating in nature, and that's the attribute you want. Now, usually each microchip is outputs only a couple of small milliwatts, right? But usually the chip is not by itself. There is a series of chips which makes up the whole unit. It could be as much as 130 sometimes, but the chip can exceed temperatures of 85 degrees C in some cases, in aircraft companies and aircraft applications and so on. So you do need forced cooling in these cases, which is sometimes by a fan or something is the way to force the heat out. It's common sometimes, like in this application, 130 chips is common, and usually these in the substrate, right? On the substrate, 100 chips could be put in, and these chips can generate up to 180 degrees C temperature. So you're talking about serious temperature rise. So the heat sink helps to dissipate heat. So anytime you look at a product, first try to jot down what are the key attributes of that product that will be important. Also, these things usually you want to prevent any stray capacitance or leakage in electrical. So therefore, this fact of insulation is very important in these things. So you want obviously the heat to quickly dissipate, which means you want this to have high what? Thermal conductivity, which means all the discussions I had with you with each parameter, that's where that comes into play, which means you need to know what is the equation for thermal conductivity, what are the influencing parameters. All of that theory should immediately spring in your mind, because you can't blindly do the selection, obviously. So then let's, just like we did this, do this and stop here for today. We'll do the translation exercise for this. Like knowing those things, how do you do the translation for the heat sink here? So again, what is the function of the heat sink?
To cool the chip.
Cool a chip or heat sink, like it says, or dissipate heat. So that is a given. What are the constraints that you're going to withstand here? Assuming you're doing this 130 chip thing. It has to have high thermal conductivity. So basically, that is the attribute.
It has to fit inside a computer case.
So size restriction. So that is the. So I'll put that last. Size, space, fit. I'll just call it that.
Not melt below 180 C.
That is a key point. Temperature can exceed at least 200 degrees C, give it some factor of safety, for example, right? So you're going to say at least 200 degrees C in temperature. And all the dimensions, like you say, are fit. Or at least these are then called as what? Function constraints. These would be called as geometry constraints, because like he said, it has to fit in there. So what is the objective here? Sometimes these two things may come together. Oh, sorry, one more. It has to be a electrical insulator. You don't want it to conduct electric current. So objective, although we have put it up here, it has to have very high thermal conductivity. So in this case, you could even move this down to this space actually. So sometimes it could come to both those areas there. And then the free variable in this case, of course, is the choice of the material, because again, he's not telling you to stick to a certain factor or a specific material to use.
That shape, also if we were like fin shape, things like that.
So that would come up here in this constraint, again shape constraint. So you can think of specifically what options. If shape is a constraint or not a constraint, shape could become a free variable, because it could be flowing, it doesn't have to be straight fins, it could have flowy fins and things like that. So those are how you lay it out. Then based on this, what are the design limiting factors which will help you determine what kind of charts you will have to look for, right? Would obviously be the next step here. So,
I just got a question on the electrical insulator part. I've seen an awful lot of heat sinks that are not intentionally, because you get higher thermal conductivities with the metals. And the control of current and damaging events is done via either the paste that you use to attach it or the other design in the system, but you don't limit yourself to non-conductors for the heat sink. So I was just wondering what drove in this case, is that?
and that's fine, that's a good, so a lot of the things you're mentioning are very recent advances in that, right, like blending materials, changing the microstructure, providing directionality, all those things are, as you go, the product gets more and more innovative. This is like a brute force based, metallic heat sink with other basic structures in terms of attachment. So this is really conventional design, if you will. Like you mentioned, conductive paste or insulating paste. There are a lot of additives or bonding agents that go with it, or films, that even this thing could be coated with something or powder sprayed with something, right? So those are additional innovations that come about in the product. So we are not really calling those out. But your breakdown could be as detailed as that. That's a good point. I'm just giving you very conventional baselines just to make the points of setting these parameters. But no, that's not limiting that for sure. So the design limiting factors, of course, you want to see what is the maximum service temperature of the material, because that will help you eliminate a lot of materials right there, right? You also want to see what is the thermal conductivity of the materials, so like the lambda values, or also not or, and you also see the electrical resistivity of this material. So when you look up these charts for this application, they are very different types of charts than you would for those applications. So the point I'm trying to make is take any product, first think in terms of what this product does in general, put those down like a general characteristics, and then break it into 4 things for translation: function, constraints, objective, and then the free variables. That way you can start thinking of products in that way. So before you go for the day, think of which is what I will do next, is basically a material for 4. You know what a oar does, right? Just like paddle and rowing and everything. So think of that, what are the functions for that, translations for that, and then we can see in terms of how a chart is used down to how to narrow it down to the material and use that in here. So the charts that you see will all get tied to this exercise. So this is translation, then we'll talk about ranking and screening, because you start off with number of choices up here, and then you work your way down to fewer and fewer until you come down to one single final choice, right? So this is the exercise you're trying to go through in terms of down selection. The charts will help you get there in that sense. We'll also talk about material indices, like setting constant slopes for stiffness or constant slope for wave velocities, and then start ranking that in convention. So this is, I will obviously give you work around this one and the problems that I promised around that. I don't think anybody is in a hurry to receive them yet, so I'll just wait for you to work through your tests and digest it in pieces like this. So sorry to be on the 3DS, but I really want you at least to experience, even if it's a limited experience, I want you to get exposure. Then it's up to your later how much to use it.